Good morning to everyone. Today we are in the session 1 of day 5. This is the lab session. It will be on lateral control of automatic vehicles. The speaker is Mr. S.K. Swain from BIT Mesra. I'll be introducing him to you first. Subrat Kumar Swain was born in Rourkela, Odisha in the year 1983. He received his bachelor's degree in electrical engineering from College of Engineering and Technology, Bhubaneswar, Odisha, in the year 2005. He received his dual master degree in electrical engineering from Swain State University in Michigan, USA, and the other one in computer engineering from Arizona State University, USA, in the year 2009 and 2013. Currently, he is serving in the designation of assistant professor in the Department of Electrical and Electronics Engineering at BIT Mesra, Ranchi, India. He is currently on Lyon and pursuing his PhD program in control systems at Kyungpook National University at Daegu, South Korea. His research interests include control theory, shared control of autonomous vehicles, and design and analysis of fractional order controller for multivariable systems. He is currently associated in various professional organizations and is a regular reviewer of ISA transactions. I welcome you, sir, in this Atal FDP. Now I'll be introducing you to the participants. There are total 200 participants who have registered for this FDP, out of which 25 participants are from Andhra Pradesh, 46 are from Tamil Nadu. From Uttar Pradesh, we have 13 participants, 24 from Maharashtra, 10 from Karnataka, and from all other states, we have less than 10 participants. And the participants are from various fields of engineering. This is all about the participants. I thank you for joining us in this FDP. I welcome you, and now over to you.
Okay. So I'm starting. Good morning to all of you. And today I'm going to actually give a small, I can say a sort of a lab session. And the lab session will be mostly on the lateral control of automotive vehicles. And currently, I am a faculty in BIT Mesra, but I am right now continuing my PhD program here in Kyungpook National University in South Korea. So, well, as far as automotive vehicles are concerned, or autonomous vehicles are concerned, it is quite a trend right now since last decade, and a lot of work is going on in this particular field. So one of the fields in which most of the work is still continuing is the lateral control of autonomous vehicles. Okay. Yeah. So before, actually, I will not go through all those contributions, but I'll start immediately with the actually the concept about lateral control. Well, just giving you a glimpse, I can tell you that most of the lot of work has been done in this lateral control of autonomous vehicles, where it is very important that the vehicle should maintain the position, or you can say maintain the trajectory in which it is moving without either moving to the without actually having sufficient offset in the left side or right side of that reference path, as well as it should also ensure that the vehicle maintains its stability throughout its entire path, and the stability is measured through lateral acceleration. So we should always ensure that our lateral acceleration is always it should not go beyond a certain limit. It should always be always be less. And another thing that is more important is that tracking accuracy and vehicle stability. These are the two important things as far as lateral control is concerned. But the vehicle speed also plays a very important role when we actually look into those lateral control, because as we go on increasing the vehicle speed, you'll see that the lateral acceleration also goes on increasing. Okay, so that is one thing, that how can we maintain you can say the lateral control of the vehicle with the increase in the vehicle speed. So that is also and that normally happens in the race cars as well as racing vehicles. So most of the work which is right now been done, that includes different sorts of controller design. We need controllers so that you will be able to the maintain the vehicle in its right trajectory. So a lot of controllers have been already discussed in the literature, like PID control is there, sliding mode control is there, feedback linearization is there, adaptive control is there. But most of the controller designs, they actually take into consideration idealistic conditions. Okay, they don't take into consideration dynamic conditions. Dynamic conditions means, let's consider the road friction. The road friction may change, like you are moving on a level road, and if suppose I say that the friction is 1, or friction is 1, then it is fine, no problem. But if there is a change in friction, like if it goes to a low friction area, then you'll have a different vehicle dynamics over there. Like the vehicle may slip, or vehicle may actually move out of the track. So all these things are being going to be taken care by the controller. Okay. um, well, so as a result of which, this particular small work that I'm going to present now will be primarily based on the sliding mode controller design, which we can say is an effective nonlinear controller, which will be able to minimize the uncertainties and disturbances affecting the motion of the vehicle. Okay. Is anyone having any doubt? Hello.
Yes,
Um,
participants.
is anyone having any doubt?
Yes, sir.
If
Okay.
you want to ask any specific question, please raise.
Yeah. Well, um, this particular here I'm going to give you some sort of contribution which is going to be the part of this work. This particular work proposes a conventional sliding mode controller design for lateral control of autonomous vehicles. The vehicle model which is considered here is a 1D of bicycle model, that is 1 degree of freedom bicycle model. And since we are going to design a sliding mode controller, one can go ahead with designing the PID controller also, which you guys can actually try it out in the lab session right now also. But we can take into consideration two different types of controller. So let's consider that we are taking a nonlinear controller, which is sliding mode. Then the sliding surface, which is most important part of the most important part in the design of sliding mode controller. It takes into consideration the lateral offset of the vehicle. Now, this is one thing where we can actually discuss right now in the lab session, whether we can only take lateral offset or we can take heading error also into consideration. Okay, so we can actually work on both aspects. We can take lateral offset as sliding surface, and second, we can take both lateral offset and heading error as the sliding surface. Someone can take the lateral yaw rate also as one of the sliding surface also. Then the road curvature, which is here the inputs that is being the things that are input to this system as the road curvature. And this road curvature is also acts as a sort of a disturbance. Which affects the motion of the vehicle. The vehicle may actually, we can try it out with different road curvatures. Okay. And we can see how the system responds. We can see how the system actually behaves as the road disturbances or road curvature changes. Okay. And the last one, the design model will be validated on MATLAB or simulation platform under various road conditions. Various road conditions means when your friction changes, road friction changes. You can check it with high friction, we can check it with wet road, and we can also check it with slippery road, snowy road, to verify the robustness of the proportional road. Okay, now this is a schematic of our lane keeping scenario, or you can say you would like to maintain the vehicle on a particular lane. So what are the inputs to this system? Are the road curvature and the constant longitudinal velocity, Vx. Okay, you have a vehicle which is environment vehicle, which you can look it at a bold color, and the states which are being output from the vehicle or which comes out from the vehicle are the lateral offset, heading error, lateral velocity, and yaw rate. So these are ones which are actually coming out from the vehicle. Actually, and the lane offset dynamics are nothing but the derivative of your lateral offset as well as the derivative of yaw rate. Derivative of heading error. Heading error is being given as psi e. you can see the psi e. Psi e is nothing but the heading error. Okay, and it goes to the sliding mode controller. You always want that your lateral offset should be near to 0. The reference lateral offset should be 0. Okay, and so your lateral offset which is coming out from the vehicle, that gets fed as a feedback path to the positive sign. The reference is 0, so you can actually, then the error actually comes to the sliding mode controller, and your sliding mode controller is designed the way in which it is being shown. Sliding surface is nothing but E dot plus lambda into V, and lambda is the regularized parameter which which is a user's choice. You can choose according to your specifications, and your steering angle will be nothing but equivalent steering angle plus your discontinuous steering angle. Okay, now here we can check. Here I will give you an exercise to do how we can find out the equivalent steering angle. But equivalent steering angle will be nothing but the function where the derivative of your sliding surface should become equal to 0, and your discontinuous sliding mode control will be nothing but minus k times signum of s. S will be nothing but your sliding surface, and k has to be positive, and general it will give you the steering angle delta which will drive the vehicle in the presence of disturbances. These disturbances will be some road friction and all those things. Okay, and of course your road curvature also acts as one of the input, but that is also a sort of a disturbance also. Fine. So taking this into consideration, um, so now let us actually discuss a little bit about the vehicle dynamic model. If you look at the vehicle dynamic model, you see that you have a this figure actually shows you front tire and rear tire. Okay, the front tire is on the top, rear tire is at the near to the origin, the rear tire, and you look at the forces which is being impact on the front tire. You see that the front tire is being tilted to a certain angle, um, and that angle to which it is being tilted is the steering angle, which is delta f. Okay, and your alpha f is nothing but is equal to the front wheel slip angle. Slip angle means as your vehicle moves on the road, sometimes what happens is that because of the low friction, your tire actually slips. Okay, and when it slips, it makes a certain angle with respect to the velocity, and that is nothing but your alpha f. Okay, and we have the forces which is being impacted on this wheel, front wheel, that is FCF, and similarly for the rear wheel it will be FCR, and this forces which is FCF and FCR, it creates a moment. Okay, because those forces are in the, you can look into it, those one is on the back, one is in the normal direction, the rear wheel, and here is in the FCF is in the, it is for the front wheel, it creates a moment. So when it creates a moment, that moment is called as yaw moment around the center of gravity O, zero, that is origin O, which is, and you can see that is the vehicle tries to, compensate this yaw motion. Okay, by giving an by giving a alternative, or by giving a opposite angle. Okay, so that the vehicle stays in stays in the trajectory, and that yaw rate is given by W. Okay, which is around the center of gravity. Okay, and your lateral derivative of lateral velocity, which will be in the y direction, which you can look into it there. So just the way your front wheel angle turns with an angle of alpha f, similarly the rear wheel also turns with an angle of alpha r. Okay, and the distance of the front wheel, center of the front wheel from the center of gravity is given as the a, and distance of the center of the rear wheel to the center of gravity is given as b. Okay, we can take as a as to be lf and b as to be lr, also front wheel and rear wheel distance. So similarly, looking this into consideration, we can derive the dynamics of the vehicle model using Newtonian dynamics, and it is being described here in this. You can see the equations. Here you can look into it, and you can see that there are three forces which is being impacting the system. One is the lateral force in the front wheel, lateral force in the rear wheel, and there is a banking force. Well, we will not consider any banking force here in our lab session. One can actually go ahead and because banking doesn't have much effect, so we can take that as 0. And similarly, you have, so the dynamics of the vehicle model will incorporate your uh, what I can say is your rate of slip angle. Now slip angle is nothing but del dB by dt. Beta is the slip angle. What is beta? Beta is nothing but the side slip angle. Side slip angle. If you look at it, if you look at that figure, you can say that around the center of gravity, that is O, if the vehicle is moving on a road and there is friction, maybe more friction or low friction, it always actually slips a little bit. If it is a high friction, then it slips less. If it's a low friction, then there will be a higher slip. Okay, so that angle is nothing but is a slip angle around the center of gravity. Okay, so the dynamics will be nothing but the first equation, that is mvx d beta by dt plus psi dot, will be equal to fyf plus fyr plus f bank. Similarly, for the yaw moment, which will be given by iz psi double dot, and that will be nothing but iz r dot, also we can write it down, and that will be nothing but lf fyf minus lr fyr. Okay, so these are the dynamics which are there. And because we will be primarily, one can actually primarily work on linear slip angle, or you can work with non-linear slip angle. Ideally, the slip angle are non-linear in consideration, because the vehicle is completely non-linear into non-linear body. So for simplicity, let us consider that if you take as to be the tire slip angle to be linear, then your lateral force fyf and in the front wheel, and the lateral force in the rear wheel will be linearly related to your slip angles. So FIF will be C alpha F into alpha F, and FYR will be C alpha R into alpha R. C alpha and C alpha are nothing but they are the front tire cornering coefficient and rear tire cornering coefficient. They are the coefficients. So your slip angle alpha F and alpha R can be actually written as, through the geometry, you can find it out that the slip angle, that is alpha F and alpha R, will be nothing but delta minus theta, delta minus beta minus LFR by Vx. Okay. Similarly, alpha R will be minus beta plus LRR by Vx. If you look into the geometry, you can find it out always. So now, if I can expand this vehicle model, you can easily see that your d beta by dt and dr by dt becomes the expressions of that is mentioned in the mentioned in the document. You can look into the d beta by dt and dr by dt. Okay, and the front and rear wheel slip angles, through the geometry, you can find it out to be beta vx plus lfr by vx minus delta, and this alpha r will be beta vx minus lrr by vx. Okay, so this is how it should be. Okay, so up till now, anyone is having any doubt? Any questions? Good morning.
No, sir. Yes.
So can you explain that the arrows, blue color arrows and orange color arrows?
Yeah, sure. See, the orange color arrows are nothing but the direction of forces. Okay, they are the direction of forces. So if you look at the front wheel, you have something called as FCF. Okay, which is nothing but is equal to the normal force that is impacting on the front wheel. Okay, similarly, if you look at the rear wheel, there is FCR, that is nothing but the normal force acting on the rear wheel. Okay, now because the front wheel is, because we are going to take the front wheel into consideration, because when you take a turn, when the car takes a turn, the front wheel we are taking, you can say that the front wheel first takes a turn, so the that is given by delta F. Okay, that is nothing but the steering, that is called the steering angle. But if there is any friction, then of course that delta F will be incremented by a little bit. That means the tire will slip. Okay, if there is less friction, and that extra angle to which it slips is given by alpha F. I hope you understood. Okay.
Yes.
Okay, fine. And the blue arrows are most probably nothing but the slip angles. They are the angular contributions angular contributions on the tires, and the orange arrows are nothing but the forces impacting on the wheels. Okay, so with all these things into consideration, this is 1DOF bicycle model to be taken into consideration. Let me actually explain you why it is called 1DOF. You see, the front tire which is being shown over here is nothing but the combination of the two front tires, that is left and right. Okay, it is a combination of two front tires, left and right. and you can actually club it up as one. Similarly, the rear tire which is being shown here is the combination of the rear left wheel and rear right wheel. Okay, so that is the reason why it is called as 1 DOF bicycle model. If I want to take it as 4 DOF bicycle model, then you will have 2 front tires and 2 rear tires, and the dynamics will be even more complex. Okay.
Okay, sir. Thank you, sir.
Okay, fine. So for this particular lab exercise, let's consider that you are taking some bicycle model parameters. So let us consider that you are taking the mass of the vehicle. The values are being given to you here. We will be using it for our simulation purpose. Okay. One can actually ask a question. Everything is okay, but later on, actually, if you try to explore a little bit more and go deep into it, one can actually ask a question. How can we find out the front tire cornering coefficient, C alpha F and C alpha R? Well, that is a good, I can give you that sort of an exercise to do. If you change that C alpha F and C alpha R, what effect it actually has on the vehicle dynamics. Okay. I can give that as a sort of an exercise to you, because I can give that. I can give that as an exercise so that you can explore it by yourself. But C alpha F and C alpha are very important, tire cornering coefficient, and that changes. Okay, as the vehicle speed changes, your C alpha F and C alpha R also changes. But because we are taking the longitudinal velocity has to be constant, I have taken as to be C alpha F has to be this value and C alpha R has to be this value. Okay, but one can actually explore more deep into it also. Okay, so with this into consideration, this is actually the variation of the slip ratio with respect to lateral force. Okay, so you can look into it and you can see that as your slip angle increases, you can take an absolute value also. As your slip angle increases, you see your lateral force impacting on the vehicle becomes more. That is quite natural also, right? If you go on a slippery road, your lateral force acting on the tires will be quite more. Okay, so this is the feature of the slip angle with respect to the lateral force. Okay. Similarly, the lane offset and heading error dynamics, that means the lateral offset dynamics, can be also expressed as the expression which is given here, where Vy is the lateral velocity, Ls is a look ahead distance. Look ahead distance is nothing but how far the vehicle is going. There may be sensors which will be able to identify like up to what distance the vehicle can actually identify or vehicle can compensate the error, lateral error. Okay, that is given by Ls. Okay, so that is done by the proximity sensors which is being fit on the vehicle. And psi dot is nothing but your rate, Vx is a longitudinal velocity, and psi e is nothing but the heading error. Heading error is the angle to which the vehicle is heading to. Okay, because of the disturbances, this angle to which the vehicle is heading to may also get affected. So that rate at which it gets affected is given by your rate minus rho Vx. Rho is nothing but your road curvature. Okay, and Vx is a longitudinal velocity. Okay, so taking this into consideration, I will first of all ask each and every one of you, is everyone there right now with me? Hello? 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 Hello?
Sir.
Yeah,
Hello,
is
yes.
yeah. So okay, so with this into consideration, I will rather ask all of you to actually, if you guys can actually if you have any pen and paper, or if you have some sort of computer, can you guys actually develop this particular one in your computer, I mean your Simulink? I have the parameters which is being given to you. I will of course I will show you the entire model and how I have done it, but what I want is that because it is a lab exercise, I really like that you guys can actually start up and do it in the Simulink. The parameter values are already given to you, these things. Okay, so is it okay if you guys want to give it a try?
Participants?
Yeah, you guys. Yeah. Because it is a lab exercise, so I would like that every one of you to start working on this model. Okay.
Okay, sir.
Eventually I will show you as to how it is done. It is little complex, but I will show you, but at least give it a try. The vehicle dynamics is being given here. So especially this d beta by dt and dr by dt, these are the two equations that you will be taking into consideration, and the other two equations will be nothing but this yl dot and psi e dot, okay, which I have mentioned it over here, all this. So please go through this model and work on it in Simulink and tell me if there is any problem. And if anyone is interested to do it in the MATLAB code also, they can write it down. Well, I have done the Simulink part, but if anyone wants to write the code, they can do the same thing. No problem. Both will give the same results. Don't take the banking into consideration, okay? This g sine phi by vx should be 0. Don't take that g sine phi by vx. Just take the basic model.
Block would be this.
Yeah.
In sim.
Yeah. Your vehicle model will be these two equations. That is d beta by dt and dr by dt. Okay. This will be the vehicle model, and the extra two dynamics will be given by this yl dot and psi e dot, which is lane offset dynamics. Okay. So first design these two, and then we can go ahead with designing SMC. But that SMC needs pen and paper. You guys have to actually work on that pen and paper. Then only you will be able to find this delta EQ. Okay, that is equivalent control.
Sir, cannot do in Simulink. Cannot find the procedure.
Cannot find the procedure in Simulink. What is the problem that you are getting? What is the error message?
Sir, error is not. I opened Simulink,
Yes.
and how come I will take this block? Actually, I have to take some blocks, na?
Yes, I'll show you. Okay. So, acha, every one of you has taken a note of these parameters equations so that I can close this. If you guys have actually taken a snapshot of this slide as well as this particular slide, then what I will do is that I will close this presentation and I will open my MATLAB so that I will show you.
Sir, we have taken, sir.
You have taken? Okay. So I'm closing this right now for some time. Okay. So here we see. Is it visible, everyone?
Yeah, that's it.
Okay. So first of all, go to Simulink, and in the Simulink, open the. Okay, I'll show you this one. When you go here, you have something called a Simulink library. Okay, this is 2013 MATLAB. Okay. Once you open the Simulink library, then there will be something called as new window. In that new window, you will be able to open this. Okay. If you guys have facing any other doubt, let me know.
So please, you can proceed, sir.
Yeah, now you see. Okay, so I will give you some hint actually how to do it so that you can start up. See, what equations you have.
I have d
Okay.
beta by dr.
Okay,
Yes,
so so just let me look into that equations now. So sorry. So you have these two equations, okay? d beta by dt and dr by dt. Okay,
Yes, sir.
fine. So let us first of all look into this one. Okay, first let's design d beta by dt, then we'll go with dr by dt. Okay,
Okay, sir.
so you see, I don't know if even if I zoom it, it will not be able to visible. I think this is a little bit. Just wait a minute. Let me see. Control plus. Okay, you guys are able to see R now. This one.
Yes, sir. It is
Yeah,
visible now.
yeah. So
Yes.
this is your rate. Okay, and this is slip angle. That is that is beta. Okay, so if this is beta, then what should be this one? Can you tell me if this is beta? Beta I'm getting it after integration of this. So what should be this value? This value should be d beta by dt, na? Okay. Hello. Is everyone getting it? Hello.
Yes, sir. It's derivative of the.
Yeah. So the derivative when integrated, you'll give you beta. Okay. This is derivative. So if you look at the derivative part, the derivative is nothing but the combination of these two parts. That is this one, that is minus r, then this c alpha f by mbx, and then c alpha r by mbx. There are three components which actually on addition will give you d beta by dt. Okay. So here you see the first part, there are two parts. Okay. Three parts. Okay. So let me first go for the first, this one. Here you see this one, this particular part. If I look into it, you see what is the dynamics that you have. You have something called a C alpha R by MVX into minus beta plus LRR by VX. Just focus on this particular part only. Okay, C alpha R by MVX. You see, this is C alpha R. This is C alpha R by M. Okay, 1 by 2250. Okay, and C alpha R has to be divided by VX, and the VX will be nothing but it is coming over here. You see, I'll show you. Just wait a minute. This is C alpha R by M. So C alpha R by N comes over here and it is divided by Vx. So Vx is this particular portion. Okay. So if I go through it, Vx is what? This one, which is divided. So this comes here.
Sir, in the tabular column, you have given that C alpha R as 38,250, sir.
Yeah, 38,250. Yeah, here you see. Okay.
Okay, sir. Okay.
Okay. So C alpha R divided by M goes here and then divided by Vx. Vx is this value. You see?
38,250 is consecutive constant.
Okay. So this is Vx divided by Vx. This part is understood. Hello, is this
Yes,
part
sir.
understood? Yeah, this part is understood. So C alpha R by MVX, you got the idea. This is C alpha R by MVX. So what is multiplied with C alpha R by MVX? That is minus beta plus LRR by VX. Okay. So now go ahead with this one. Now let's consider this. This part everyone understood it. This part everyone understood it. So let's consider this particular portion. Okay. So this portion, first of all, let's see. The first portion is what? The first portion is minus beta and then there is LRR by Vx. Now here you see, you have LR, this value, and it has to be multiplied with what? R. And R comes from where? That is your rate, right? And this is coming from here. You see, this R value, this one, this one, this one, and this R is nothing but coming out from here. And what is this? This is nothing but R dot. Okay, this is R dot. sorry, this is not r dot, this is r dot. So r dot integrated will become r. Okay, and this r will get multiplied with lr. Okay, which is nothing but this thing, lr, and this has to be divided by vx. Okay, and this is divided by vx. Okay, this is divided by vx. Okay, so you get this is nothing but lrr by vx. Okay, and this portion is nothing but beta minus beta. What is beta? Now here you see, this is where you are getting beta. Okay, now this beta, if you take this into consideration, this is the beta which is coming here and it is getting subtracted, so this becomes minus beta. So minus beta, so you have minus beta plus lrr by vx multiplied by this. So you got minus this portion and multiplied with this, you get this value. Okay, so you got this value. So once you get this value, sorry. So once you get this particular value, the entire thing, let's consider this particular portion. Okay, so we are already done with this, so let's consider this portion, okay, which is the first term. So in the first term, what is the first component of the first term? That is nothing but minus r. Okay, and the minus r is coming out from here. You see, this is r, and the r is coming from where? This portion. Okay, that is your rate. This portion, this is where your r is coming. Okay, and this r is multiplied with minus r, minus 1, it becomes minus r. Okay, so minus r goes here, and then you have this two term. Okay, this particular term, and this particular one, delta minus beta. Okay, so you already got this value minus r. Now this is the value. Okay, so before that you have to first identify what is this values, that is c alpha by mvx. So you see, so you have c alpha f, okay, this value, okay, and this is divided by m, and then this is divided by vx. You look at it, this is divided by vx. So you have c alpha by mvx, which goes here, and that gets multiplied with what? This value, delta minus beta minus lfr by vx. Now that has to be multiplied by delta. Now what is delta? Delta is the steering angle, which you will get it from the sliding mode control. Okay, so this is delta. Okay, so this is delta, and from delta, and this is what is minus. This minus is nothing but is equal to beta. Okay, and this value is coming out from here. This value is beta, which is coming out from this value. You see, this is beta, so this is subtracted, delta minus beta, and after delta minus beta you have minus lfr by vx. So this portion is lfr by vx. If you look at this particular portion, sorry, this portion, this is beta, this particular one. So this one, you see, this particular one, so you have something called as, this is nothing but vx, and this one is coming from lfr. Okay, so this gets subtracted and you get this term, which gets added with minus r to get this component, and then you will have these two dynamics already covered up. Everyone understood how it is done?
Sir, is that delta value is a constant value, sir?
No, delta is not constant.
Varying.
No. Delta is the one steering angle which you will get it from the sliding mode control. Okay, design of sliding mode control. Yeah. So as of now, just make sure that your delta is coming from, delta is an unknown entity. You just you can take it a constant value and you can just substitute. Right now, let's consider that you are not designing any sliding mode control. Let's consider that you are just taking delta as to be a fixed value as 0.3. Okay, 0.3, and then taking that, please design this model.
So first we have to assume some constant value. After that we have to design.
Yes, first take delta as to be 0.3 and design these equations.
Okay, sir.
Okay. And then after you have designed, execute it, and then we will see the verify the results.
No audio, sir.
Yeah. Is it audible now? Hello.
Yes,
Yeah,
audible.
yes.
Yeah. You first of all design it, and then I will execute my MATLAB Simulink simulation, and we will verify the results. And for the this one road curvature, take this road curvature value. If you guys are having take the road curvature value as 0.001, this value 0.001. Okay, this value. Hello.
Hello. Yes.
Hello. Yeah. Students, are you able to get some idea from it? I'm actually going to demonstrate one small exercise, same thing.
Sir, please demonstrate because still can't do.
Okay, fine, no problem.
Still
Okay,
stuck.
okay, no problem. I'll show you. So let me actually have a. Actually, I will just remove this delta. Okay, and I will take this as a steering angle. This 1.3, and anywhere else which is where delta is required. Yep, looks fine. So this one is okay, and delta value has to be this one. Okay, so let's run it. Just wait a minute. Okay. Fine. Yeah. Did you see now the plot? That is the this is a XY plot. This is how this is the plot of your velocity of vehicle in the x-axis with respect to velocity of vehicle in y-axis. Everyone got the idea? Hello.
Yes, sir.
Yeah. Now you look into this one. Okay. So let's consider the slip angle. Okay. And here, what you have done here right now? Here you have taken this. Taken the steering angle has to be constant 0.3. Okay, so now you see the slip angle. You see this one. You see the slip angle. Okay. So just look at the slip angle and tell me what should be the ideal if a vehicle is moving on a road. Do you want the vehicle to slip?
No, sir.
So you see that here when the vehicle is moving with a constant steering angle, How much is the slip angle in which it is settling down? Minus 0.04, right?
Yes.
Okay, so that means, but it should be ideally to 0. It should go down to 0, or it should oscillate around 0. Okay, fine. But what it is happening right now is that it is maintaining a constant offset of 0.04. Why? Because we don't have the requisite control to bring this slip angle near to 0. Got the idea? Okay. Okay.
Sir, can you repeat again this one?
Okay, tell me. See, here you are using using constant steering angle. Okay, 0.3. Okay. Now, because of this constant steering angle, just think about physically. Okay, just think about physically. You are driving a vehicle, and you have turned the steering wheel, constant steering wheel angle 0.3. That means your steering angle is your steering wheel, that road steer wheel to the left steer wheel is turned at a certain angle which is 0.3. So what will happen? It will always stay at 0.3 now. So what will happen?
Yes,
It will not track the trajectory. It will go out of the trajectory.
yes, sir.
Okay, since it will go out of the trajectory, it will maintain a offset. Okay, maintain a lateral offset from 0. That is what is happening here. This is a slip angle. Anyways, it is the slip angle, and I'll show you the yaw rate. Yaw rate is the oscillations around the center of gravity. So yaw rate, see, this is also maintaining a constant value. Okay, 0.8. And let's look at the your lateral offset. Lateral offset is how far it is from the reference trajectory. Reference trajectory should be 0. Okay, because it should not be it should not have higher lateral offset. But you see the lateral offset is increasing, right? Okay, because lateral offset is increasing means what? The vehicle is diverted. Vehicle is completely it has diverged from its reference position. Reference position should be 0, but it is going to 400. Okay, that because your steering angle is not controlled, it is uncontrolled. It is a fixed steering angle which actually doesn't allow the vehicle to come back to the reference position. Okay, so this is the lateral offset. Okay, this is the problem. And then what is the steering angle that you get? Okay, I haven't actually added this steering angle. Let me add this steering angle here, and I'll execute it once more. We'll see. Okay, here you see. Okay, the steering angle is by default it is 0.3. Okay, this is quite simple, 0.3. Okay, fine. So now the question comes here. So what did you I wanted to ask you one question. So if you drive your vehicle at 0.3 steering angle, what are the things that you noticed?
Hello.
What are the things that you noticed? That means what are the problems that you faced? Can anyone tell me?
हॅलो ते टीमच्या ग्रुपमध्ये मला ऍड कर केस ते सेन्सर आणि डिजिटल लॉजिक घ्यायचं ना.
Hello. My question
ना.
Yeah, my question to all of you is, you saw the results, right? You saw the results of the simulation, right? Hello. Hello. Am I audible now?
Yes, sir.
Yeah,
Yes, sir.
all of you saw the results right now, right? I demonstrated you in front of you with a constant steering angle. What are the problems that you saw right now with this simulation? Can anyone tell me? Even one point also, it's okay. Anyone can actually tell, like, what are the problems that you faced here? Was your lateral offset 0?
No.
No. And what should be your ideal lateral offset? It should be 0, right? The vehicle should always move on the trajectory. It should not have any offset, but it was not 0. Rather, it was very high value. We should always want that our side slip angle to be near to 0. But was the side slip angle near to 0, beta? No. Okay. It was a constant. It was a constant side slip angle. Okay.
Yes.
Similarly, if you look at the
कितना
yaw
बोला था
rate,
आवाज ही ना
is anyone actually, there is some sound coming up from somewhere. Please unmute the mic.
कौन
If
बोलने
anyone.
लायक कोई
May I request all the other participants who are not responding, please turn off your mic.
Okay, so thank you. So if you look at the yaw rate, okay, the yaw rate was also not controlled. Okay, so this happens basically because you are not controlling your steering angle. Okay, this is happening without the design of a controller right now. This is the uncontrolled portion. So this actually gives us an indication that we need to design a suitable controller. Okay, fine. So let us, the next portion will be how can we design a controller for this particular small exercise. Okay, so now I'll come over to this portion. Okay, so now let's go ahead with this controller design. Okay, now here I have taken as to be the lateral offset, that is YL. Okay, has to be nothing but is equal to the error will be nothing but is equal to YL minus 0. 0 is the reference trajectory. You want your lateral offset to be 0 reference. Okay, so the error will be nothing, E will be nothing but is equal to YL minus 0, so will be YL. Okay, so sliding surface will be nothing but YL dot plus lambda times YL. Lambda is the user specified constant which you can design it. Okay, I will show you in my simulation what value of lambda I have taken. We can take different values of lambda. Okay, and that we will demonstrate it later. First of all, you understand this. So the sliding surface will be nothing but is equal to YL minus 0, YL dot plus lambda times YL. So if S is equal to this value, how will I get the equivalent steering angle? Equivalent steering angle will be nothing but the function of S dot equal to 0. That means if I first of all solve this S is equal to E dot plus lambda E, and then find the derivative, and then I equate it to 0, and then after I've equated it to 0, you separate the delta portion, and whatever portion will be left behind, that will be nothing but equal to delta equivalent. Students, understood this portion? Hello.
Yes, sir. Yes, sir.
So what I really want from you, because this you don't need simulation here, this you need pen and paper. What I want is that I will show you what is my delta equivalent, but I want you guys to first write it in pen and paper, solve it in pen and paper, find delta EQ. So your S is nothing but is equal to what? Error will be what? Error will be YL minus 0, that is YL. So S will be nothing but YL dot plus lambda times YL. So what will be S dot? S dot will be E double dot plus lambda E dot. E double dot will be what? YL double dot plus lambda times YL dot. Okay, you already have YL dot equation this. Okay, and if you want to find YL double dot, it will be Vy. You have to again find the derivative of this. Remember, this Vy is nothing but beta times Vx. Okay, Vy is nothing but beta times Vx. I haven't mentioned here, but wait a minute, let me show you. Okay, okay, here you see you have this beta, right? So if you multiply this beta angle, this beta side, that is side slip angle beta, with Vx, you will get the lateral velocity Vy. Okay, so instead of this Vy, you can write beta multiplied by Vx. Okay, so you can so please do this exercise. Find S with respect to YL. So it will be YL dot plus lambda YL. Then equate S dot equal to 0 using these dynamics and find out delta EQ. Then I will go for the next part. You do it in the pen and paper, and once it is done, then let me know. I will actually switch over to the Simulink. Students, every one of you understood the concept, right? Hello. Yeah, every one of you understood the concept, right? This is the equivalent steering angle, which you will get it by equating s dot equal to 0. And after you find it out, I will discuss about the discontinuous steering angle, which will actually control the discontinuous portion. Okay.
Excuse me, sir.
Yeah.
So how do we tune the parameters of the sliding mode controllers?
Okay. First of all, I will show you. Have you actually found out delta EQ?
Sir, I'm trying to find,
Okay.
but actually a question arises in my mind: ki how do we tune these parameters? How do we decide the values of these parameters?
First of all, what all are the parameters here in this sliding surface design? K, na?
Yes, sir.
Right?
K.
K.
Yes.
So you have to find out what should be the value of K, or what should be the range of K, such that your system is stable. Okay.
Okay, sir.
And for that, what you have to do is that you have to find out the Lyapunov equation. You have to find the stability of the system. So you have to check it through Lyapunov. What should be the range of K? Okay, I will tell you that one also. But first, find out delta EQ. At least if you are able to find delta EQ in a rough way, also just let me know. Then I will switch over. Okay.
Okay. Thank you.
Yeah.
Sir, is it time derivative of delta x, sir?
Time derivative of delta x? No. It should be the time derivative. You have to find out s dot with respect to t, ds by dt.
Okay. Okay.
Okay. Every one of you, please pay attention. Hello. Hello. Hello.
Yes, sir. Yes. Yes, sir.
Yeah. Please pay attention and see how I have done it here, so that it will give you a hint. See, according to our figure, where is that figure? This figure, right? So what should be the error? YL minus 0, right? Okay. So here you see, error will be nothing but YL minus YL ref. What is YL ref? YL ref is 0. So the value will be YL. Okay. So your sliding surface will be nothing but is equal to derivative of error plus lambda of error. So it will be given by YL dot plus lambda of YL. So what will be S dot? S dot will be YL double dot plus lambda of YL dot. But what is YL double dot? It is a derivative of this portion. So it will be beta dot Vx plus LSR dot plus IL dot Vx. Okay, this one plus lambda YL dot. YL dot is again this value. So you get this thing. So what is S dot? Now, beta dot is what equation? Can anyone tell me what is beta dot value? I have shown you here, right? This expression. This expression is beta dot. This is R dot. Okay. So substitute that value of beta dot here. Okay, up till this portion. Substitute R dot portion here. Okay, then psi L dot. Psi L dot is this value, which this instead of N write R. Okay, that is your rate. This is your rate. Substitute it here. Okay, psi L dot Vx. Then lambda beta Vx, lambda LSR, and lambda psi L Vx. Substitute everything here, and you have to make S dot equal to 0. So when you have to make S dot equal to 0, take lambda value, that is this lambda value at one side. okay, and express all other terms minus r, then plus minus beta and all other terms, that will be equal to 0. Okay, everyone understood this portion?
Yes, sir.
Okay, because this is the most important portion of sliding mode control, because other things is quite easy, but this is the one which is important. Okay, and then you rotate I'll rotate it, just wait. Okay, so after that what you do, you take the steering angle to the left side and you compute all and take others to the right hand side. Okay, so you will have delta EQ will be nothing but is equal to, take this one to the denominator, you will have this expression. This is such a long expression, this expression. Now this is the equation. There will be some terms because of the disturbances, because of the disturbances, there will be some terms which will be not taken care by this delta EQ. Okay, the rest other terms will be taken care by delta EQ. Taken care means that will get cancelled. Okay, delta EQ will be able to have a cancelling effect of the other terms apart from disturbances. So now what is the so how will we take care of the how will we take care of the terms which are affected by disturbances? That will be taken care by delta DC, which is called discontinuous control. Understood? Okay, so if I want to find out what is the value of discontinuous control which will take care of those disturbances, yeah, anyone?
Your screen is not visible.
Oh, this is not visible.
No.
Wait, just wait a minute. Oh, okay. I haven't actually shared this one. Wait a minute. Let me see. Okay. Is this visible now? Hello?
No, sir. No, sir.
No, sir. No, sir.
It's not visible? Okay. Let me actually do
No,
it
sir.
again. Let me do it again. Just wait a minute. Is it visible now? Hello?
Yes, sir. Visible.
Yes, sir. Okay. So now you see, you got your error right, this value, YL. Okay, YL minus YL ref value is 0, right? Okay, so you get YL. So your sliding surface will be nothing but equal to E dot plus lambda of E. So what is E dot? E dot will be YL dot plus lambda YL. Okay, and then find the derivative of S. So you will have YL double dot plus lambda YL dot. YL double dot will be the derivative of this portion, and this will be nothing but beta dot Vx plus LSR dot plus IL dot Vx plus lambda beta Vx, all this value. Okay, and then you group all these values. Now what is beta dot, which I have already it is there in the vehicle dynamics, right? Substitute that beta dot value, substitute the R dot value. Okay, substitute the psi dot value. Psi will be R minus rho Vx. Okay, this is R. Substitute that value, then put all these things, and then group all values under lambda, under delta. Similarly, R values, beta values, and all other expression are equal to 0. Okay, now then you group all the values of delta to the left side and keep all other right side. So when you solve it, you get delta equivalent. Substitute this one in the denominator, you get this big portion. Everyone got it? Okay.
Yes, sir.
Yeah, once you get the equivalent control, what does the equivalent control do? Equivalent control actually cancels the effect of all those terms which doesn't have disturbances, which doesn't contribute disturbances in the expression. Okay, so then if it is going to cancel the effect of those terms which doesn't contribute disturbance, then what will be the other terms left behind? The other terms that will be left behind is the terms which will which will have the effect of disturbances. So what? So we have to have an extra term along with delta EQ, which will compensate those terms which is having disturbances. That is taken care by delta DC. Okay, and how will we find delta DC value? So for that we have to find the Lyapunov function. So Lyapunov function, everyone understand what is Lyapunov energy function? Okay, so that will be nothing but is equal to is an energy function which has to be always strictly positive. So make it half of s square. Okay, so s square is greater than 0. So this is a positive value. So find the derivative of Lyapunov. That is a time derivative. Remember, time derivative of Lyapunov function. So that will be nothing but is equal to s into s dot. So s value will be this, and what will be s dot? Now this is where a trick comes. When you want to find s dot, now you see in the s dot all these expressions are there. These big expressions are there. But tell me one thing: if delta value is nothing but is equal to delta EQ plus delta DC, and if you substitute this delta over here in this expression, can anyone tell me if they substitute that delta over here, will all other terms be cancelled or will it not be cancelled? Hello? Hello? Am I
Can you
audible?
repeat the question?
My question is, if you substitute this delta value, because you are getting s into s dot now, s is like that, s dot value you have to substitute. So if you substitute this delta value here in the s dot equation, here in this s dot equation, here this delta over here, if over here and over here, if you substitute that delta value, which includes the delta EQ also, that is equivalent one, so will all other terms be cancelled or not? Because why? Because delta equivalent you are getting it when you equate these two terms now, you get this expression. When you substitute this value, this delta value which has this delta EQ component, and delta equivalent component is this expression over here, that delta EQ will cancel all these terms or not? It will cancel those terms now, because you are getting this by equating it
So
to
it will
0
be
na?
cancelled all the terms.
Okay, once that is cancelled, then what is the thing that will be left behind? Only discontinuous term will be left behind, right? Okay, okay, only that discontinuous portion, and that discontinuous portion of the control will be multiplied with how much? That will be multiplied with this CF by MVX and with this expression LS LF by IZ. Okay, so that is what this one. If everyone has got it, just let me know. Don't worry about this expression. Don't worry about this expression. This I wrote it just for my reference only. Please don't get worried about that. Gets cancelled. All other things gets cancelled. Only thing that is left behind is delta DC multiplied by this expression. This one. Okay?
Yes, sir.
Okay. Now tell me one thing. Whoever has understood, just tell me one thing. If I want to find out, sorry, this one. I'll make it this one. Now, if S is into delta DC this. So if I substitute delta DC is equal to minus K into signum of S. Okay. Just wait a minute. Okay. Minus K into signum of S, and your signum of S can be written as, why I have written like this, you can directly write signum of S also, but if I write it as S by 1 plus mod of S, it will remove the chattering. Okay, that oscillations. Okay, this is a modified version. So if I write this and I substitute it over here in this expression, then what I will get? I will get nothing but is equal to minus K S square. Okay, I will get minus K S square times 1 plus mod of S multiplied by this expression. Okay, now S square is positive, 1 plus mod S is positive, and this expression is positive. Okay, but how much? What should be the value of V dot? Can anyone tell me? If V is strictly
Sir,
positive,
it should be negative, less than 0 for the system to be stable.
so what should be the value of K here?
K must be positive.
Yeah. So the value of k has to be greater than 0 because all other values are positive, right? S square mod of s and this expression, right?
Yes, sir.
So your system will be stable only when k value is greater than 0. Now the things are clear.
Yes, sir.
Okay, this is how you find the value of k. This is how you find the value of k. This is the most important thing in sliding mode control, checking the stability criteria. If you otherwise, if most of the students what they do, they just manually tune the value of k, which is completely wrong. Understand? Okay. The next thing that we will do, probably not now, maybe in future, what should be the range of k so that you will get optimal value. That will be much more better. Okay. Anyways, this value is k greater than 0, the system will be stable. Okay. So now let's go for the control portion. So you got the design of this one, and so let's come over here. So you got the value of k, you get delta DC, you got delta equivalent, you get delta, and then you will be able to control the vehicle. Okay. So now let's go over to the our this one. This is visible. Hello.
Yes, sir.
Okay. So now let's work for the sliding mode control. So I will remove this 0.3 term. Okay. And I will take this which steering angle. Just hold on for some time with me because I have removed this thing. Come on. Okay. So this part sorry. Okay. So this is a steering angle. Now here I have to have YLD and YL as expression. Okay. So I'll tell you here what I have done. You have designed all the things. This is where you have to design this value, which is your this expression YL dot and psi E dot. This thing you can design it here. Okay, here. Okay, so you have beta into Vx plus Ls into N plus IL into Vx. This is a look ahead distance. You can change this value also. Look ahead distance means how far you are looking as a driver or as autonomous vehicle, if it is having sensor, how far the vehicle is going to sense to its nearest distance ahead, such that it will take the correct action. So this is variable depending on the sensor's capability. Okay, this thing can actually change. Okay, and what sensor is actually specifically which sensor takes care of this? This is called proximity sensor. This will take. So then you find YLD as this expression. Once you get YLD, and this is called as the heading error. So heading error, you already have got the expression of heading error. This thing psi minus rho Vx. So you get it here, n minus rho Vx. Okay, and then you find the derivative and you substitute it here, you get YLD. If you get YLD, what is our
Excuse me,
expression of
sir.
YLD? Yeah,
Sir,
yeah.
your slide is visible only, which is having the graph between slip ratio and lateral force.
Oh, okay. So this MATLAB is not visible, right?
No,
okay,
sir.
Okay.
No, sir.
Okay. Okay. I'll do it now. Just wait. See. First of all, over here, you look at this. This is PSI-LD and this is YLD. Okay, YLD and PSI-LD are all. These are the dynamics equations, which is already I have shown you in the diagram. I have shown in those dynamics are already there. Now this is the one where you are to find the sliding surface. Okay, what was the equation of sliding surface? Can anyone tell me? If you look at the expression, what was sliding surface? Sliding surface was E dot plus lambda of E, right? Okay, fine. So E dot plus lambda of E. So you have to find derivative of E, and lambda is the regularization parameter multiplied by error. Okay, so you get sliding surface S. This expression is being designed here in this expression. So what are the parameters for which you need SS? If you look at this sliding surface, here, S value, you need YL dot, that is a derivative of YL, lambda value, and YL value. So these three parameters are required to find S. So you have YLD, YL, and lambda. And lambda, how much I have taken? 5. So you get sliding surface. Once you get sliding surface, what will be the discontinuous control? The discontinuous control is minus K times signum of S, or minus K S by 1 plus mod of S. That is what is being expressed here. So you get delta T, that is discontinuous. And to find out delta continuous portion, sorry, equivalent portion, how much is the equivalent? Is this big one. Okay, is this big expression. Okay, this big expression. This big expression, you design it here, and you add both of it. Delta this and delta this. This you add both. When you add it, it becomes your delta, which is the actual steering angle. And that actual steering angle goes here. You see, this actual steering angle and this value. Understood? Okay?
Okay, sir.
Okay, got the idea? Now, let us now see what happens. Earlier we saw that when we are putting a constant value, it was not tracking. Okay, the lateral offset was getting very higher value. Slip angle was not coming to 0. Now let us see what should be how the expressions come now. Okay, what are the figures right now? So I have already plotted it. I will show you now. So you see, when I am actually taking the fixed road curvature as 0.001 with sliding surface, now you see if you look at this particular portion, okay, that is the, what is it actually? I can't actually look at it. Just wait a minute. Okay, so this is the slip angle. If you look at the slip angle, everyone is saying the slip angle is coming down to 0. Okay. Hello. Hello. Hello.
Yes, sir.
Yes, sir.
Yes, the slip angle is 0. The yaw rate is again coming down to near to 0. You see all the values, and you see this one. This is nothing but your lateral offset. The lateral offset is coming down to 0, which was not 0 earlier. Remember, it was going down to 400 when there was no control. But now you see it's coming down to 0. Okay, and the yaw angle, you see, yaw angle is, because it is a constant curvature. So the you think about it like this: if it is a constant curvature and your wheels are turned at a certain angle, it will always move at that angle. It will always head at that particular angle. The vehicle will always go on in that particular direction. That is why it is a sort of a ramp. It is making a certain angle with respect to x-axis. Okay, fine. And this is the sliding surface. Okay, remember what is sliding surface? What was my sliding surface? If I showed you what was the sliding surface, my sliding surface was this equation. So tell me one thing, students, what should be your lateral offset in general? What should be your lateral offset ideally? Hello, what should be your lateral offset ideally? Am I audible? Hello.
0.
It should be 0. So YL dot will also be 0. So sliding surface should be 0. Okay. So now you see what is the sliding surface here? It is having very minimum oscillations coming down near to 0, 10 to the power minus 3. Okay. So that satisfies our specifications, and this is the steering angle. You see, earlier the steering angle was not coming down to 0. it was a constant value at 0.3, but now you see it is having it was having little oscillation, again coming down to 0. Okay, this is the effect of this is how you are able to design a sliding mode controller for controlling the lateral motion of the vehicle. Okay, this is with fixed road curvature, rho is equal to 0.001. But if you take a sinusoidal road curvature or a different road curvature which oscillates, then you will get this type of structure. You see, this is the road curvature now. When you take this road curvature, now your slip angle will it will oscillate a little bit, but it will not be much. You see, it is 0.01 minus 0.01. It is oscillating around 0 position. Okay. Similarly is the yaw rate. Now you see the lateral offset is again coming down to 0. Yaw angle is, you see, this thing because of the curvature. Sliding surface is almost near to 0, and steering angle is oscillating little bit but near to 0, around the 0 portion. Everyone got the idea? Hello?
Yes, sir.
Yeah. So what did you infer from all this from the design of controller? Can anyone tell me? What did you all infer from? What was the difference between when the controller was not designed and when the controller was designed? What did you see? What did you infer? Hello.
We set point tracking and disturbance rejection. These are the two main effects of the controller.
Yeah, so that you are so based on different road curvatures, you are able to control the motion of the vehicle, make the lateral offset near to 0. Other parameters like yaw rate, slip angle, all are coming within range. Okay, now one thing actually I will tell you, which you can demonstrate it in your home, because you are right now going to have time so that you can demonstrate it totally. Think about it like this. Let us consider that you have some disturbances which is affecting the vehicle. That means you change here. I'll tell you one thing. You look at this dynamics, okay, here in this particular dynamics, okay. Remember that this dynamics where it is C alpha F is there, na? This is associated with a road friction coefficient mu. Here the mu value is 1. That is why it is written as C alpha F only. But actually it should come as mu. Okay, similarly here also it should come as mu. I have taken the cases where mu is equal to 1. In your home, please try it out when mu is equal to 0.7 and 0.4. Understood? Okay?
Yes, sir.
Try it out, because what do you mean by 0.4 and 0.7? 0.4 means when the vehicle is moving at a low friction surface, almost on a sort of a snowy surface. 0.7 means it is moving on a cemented surface. Okay, so try it out. If the value of mu, just put here mu as 0.7, 0.7 or 0.4 and 0.4. Of course, you have to change your delta, your equivalent control. In the equivalent control, that mu terms will also come. So change accordingly and see whether your responses are coming like this or not, or constant or road curvature. And for this, what does this mu, if you change the value of mu, what does that actually acts as a sort of a disturbance only. Okay, fine. Those,
yes, sir.
Yeah, those extra decrease in mu is coming out as disturbance, and that will be taken care by sliding mode controller. Okay, why am I would have shown this one, but unfortunately this is not getting visualized. I'm in my MATLAB. No one is able to see my Simulink, right?
No, sir. Sir, can you send the Simulink to our mail IDs?
Okay, I will do one thing. I will just send this one to, if I have your email IDs, then I can actually send this entire one to all of you. Okay?
Yes, sir. Thank you so much.
Sir, anyway, you have to send the materials to me so that it can be shared with the participants.
Okay. So participants did you get any sort of an idea how to design sliding mode control? Actually, there are a lot of other things also. Like this is just This we have designed it with respect to, I told you how to do it with different road friction coefficients. You can add some wind parameter also, that is crosswind parameter also. You can add different longitudinal velocity also, Vx value if it is different. Okay, you can change Vx values, variable Vx also you can check. So different lot of other research things can be done. Okay, you can add some longitudinal dynamics also. So many things are there. So I would encourage all of you to, if anyone is interested in this subject or in this research work, to carry on with this this type of fundamental works, and see and elevate your knowledge, as well as try to think of like in physically also in the real world scenario, if your vehicle is moving autonomously, then looking at the research papers or looking at the works that has already been done, how can you contribute in this particular area? Actually, there is other field called shared control also, which is my research area, okay, in which the driver also comes into play along with the automation, where driver automation has to work in unison, okay, in collaboration. That is a little difficult thing. There is a next part, okay. So try to think about it, and it is a very interesting and very evolving area, okay. So I think it will be a good thing for all of you, and I will share all the materials also, especially the books and the standard book, as well as the Simulink results, the PPT file and the Simulink file, okay, the .mat and .m file and .slx file, all of it.
Thank you, sir. Sir, can you share your mail ID also?
Yeah. I will share. I will send it to Vijayalakshmi ma'am. Okay? So that
Okay,
if
sir.
any one of you is having any, unfortunately, actually, since I am outside, I am abroad, so I am mostly free in the weekend time. That is either in the night time in weekdays or in the weekend time. Otherwise, my entire time goes in the lab only. So I won't be able to give you a response probably in the daytime, but in the night time, if I get, I will be able to give you the reply. Okay?
Okay, sir. Actually, I am working on this sliding mode and chattering effects of this sliding mode control. So,
Yeah. So I
if
hope
I
like you.
contact you.
Yeah. So I hope you got an idea as to how to design the sliding surface, how to check for the gain value, stability value. How
Yes,
can
sir.
you check?
Actually, I am working in the tuning of the parameters and the effect of reducing the effect of chattering in sliding mode control.
Okay. Oh, that is a good thing. That is a good thing. So there are a lot of other things are also there. If you have any doubt, you can reach out to me. Okay.
Okay, sir. Thank you.
Okay. Yeah. Good to talk to all of you. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.
Yeah. Welcome.
Thank you, sir.
Welcome.
Yes.
Yeah.
So anything more?
No, ma'am. I'm right now keeping up. Okay. I'm signing off, ma'am.
Okay. Thank you, sir.
Okay.
Thank you. Okay.
Thank you, sir. Thank you for joining.
Thank you. Yeah.
And you please share the PPTs with the participants.
So
just send it to me. I will share it with the participants.
Yeah, I'll send it today. Okay.
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 Thank
ma'am.
you for joining.
Okay, ma'am. Thank you.